In the previous class, we introduced momentum space and how the momentum operator behaves in momentum space. We have found that momentum operator behaves in momentum space just like a position operator behaves in position space. Now, logically, the next step is what is the behavior of position operator in momentum space. Okay. But before going to that, to analyze the behavior of position operator in momentum space, we have to consider this idea, transformation function. Transformation function means how we can move from momentum position basis to momentum basis, or from momentum basis to position basis. After that, we will take up the logical thread and we will consider the action of position operator in momentum basis. Okay, so what is the idea of transformation function? In one of the previous classes, we have studied how we can get a change of basis from an old basis set, let us say AK, to a new basis set, let us say ket DL. Okay, this may be the eigenkets of some operator, this may be eigenkets of some other operator. Okay, since these are Hermitian operators, this is a complete set and this is also a complete set. So if it is a complete set, it can be a basis set for a vector space. So we have one basis set, we have another basis set. How do we produce the change of basis from the one basis set to another basis set? This change of basis, we have studied this in detail. This change of basis is produced by a unitary operator. It's a unitary transformation and a unitary operator is required to produce this change of basis. So it changes each vector, it changes the base kets, it changes general ket, it changes the operator. We know how these changes are produced. In particular, each matrix element of this unitary operator, okay, each matrix element of this unitary operator is obtained as like this. The matrix element of this unitary operator in terms of the old basis is obtained as AK bra vector, AK ket vector BL. These are the matrix elements of this unitary operator in old basis set. So you see the structure. On the bra vector side we have old basis ket. On the ket vector side we have new basis ket. A new base ket. Okay. Now let us come to our discussion. So far we have been discussing position basis and momentum basis. Okay. This is also a change of basis. Okay. Let us see how we do this change of basis. Position basis to momentum basis. So the difference between these basis sets and this basis set is these are discrete. You can count them A1, A2, A3, B1, B2, B3. So these are discrete sets. These are continuous sets. Both the position basis sets, base kets and momentum base kets are continuous kets. There is a difference, but the idea is the same. So this is also produced by this change of basis is also produced by a unitary transformation, and the matrix element of this unitary operator. How do we get this? Inner product between these two base kets. Inner product between let's say if you want the change of basis from the position base ket to momentum base ket, then the old base ket is position base ket, new base ket is momentum base kets, and the inner product is on the bra vector side you have old base ket x prime, on the ket vector side you have new base ket p prime. Okay, let me introduce this x prime p prime here. So these base kets are labeled as ket x prime, here ket p prime. So inner product between just like this, old base ket on the bra vector side, new base ket on the ket vector side. Okay, since these are continuous base kets, okay, this type of a matrix element will be a continuous function, and this is called transformation function. Okay, we will explore it further. First of all, if you look at this, this you can express as a wave function. Okay, earlier we have defined wave function in position basis and wave function in momentum basis. See, if you have a general ket, okay, its component in position basis is defined as wave function in position basis. How do we define it? Some wave function alpha, psi alpha in position basis. This is the component of a general ket along position basis. Similarly, the component of the same general ket along momentum basis is defined as some phi alpha p prime. Now, when you look at this, this is just like these two expressions. Only difference is that it's not a general ket but a base ket. But a base ket can also be treated as a general ket. So this is the component of momentum base ket, momentum eigenket in position basis. Okay, so this also can be defined as a wave function. So using the same notation, component of momentum eigenket, momentum base ket in position basis can be expressed as, so look at this, this is just like this. Instead of ket alpha, you have p prime, that's all. So we can use a similar notation. So in order to distinguish this, distinguish it from these two wave functions, let me use a symbol u. The idea is the same. We can use the same notation psi for all, but let's use psi for wave function in position basis, phi for wave functions in momentum basis, and u for this wave function, that is wave function of momentum eigenket in position basis. So following the same notation, instead of alpha, let me use p prime, and in the argument we have x prime. Okay, so understand that this is the matrix element of the unitary operator that produces the transformation from position base ket to momentum base ket. And this matrix element is a continuous function. Why? Because these two base kets are continuous functions, and this matrix element can be called, it's a function, and this is called transformation function, and this can be interpreted as the wave function of momentum eigenket in position basis. Okay, so this is a transformation function. We can call this transformation function. Transformation function, or we can also interpret it as wave function of ket p prime in x basis, right? Wave function of momentum eigenket in position basis. Okay, so let me use this notation u p prime x prime. So understand that this notation follows the same pattern of these two notations. The ket vector symbol comes here, and whatever is the basis we are using, component in terms of the basis, that basis comes here. So here ket comes, when the ket vector symbol comes here, the basis is momentum. Here ket vector is p prime, momentum eigenket, and the component along the basis is position basis, right? Now we want to obtain an expression for this transformation function. Okay, let's call it transformation function, to keep in mind that it produces the transformation. It is the matrix element of the unitary operator that produces this change of basis. So let's try to get an expression for this transformation function. Earlier when we discussed the position basis, we have had this result, x prime momentum operator ket alpha. Basically this means what the action of momentum operator in on a general ket in position basis. Okay, and this is obtained as minus ih cross dou by dou x prime alpha. Okay, this equation means that the action of momentum operator on a general ket is in the language of wave function is, the modified wave function is simply minus IH cross dou by dou x prime acting on the old wave function. Okay, so from this we deduce that the action of momentum operator on position basis multiplying the old wave function or acting on the old wave function, this operator minus IH cross dou by dou x prime. Okay, this result we have obtained when we discussed the position basis in the second class of position basis. Okay, now what we do is, let us replace this general ket can be any ket, right? So let this ket alpha is equal to ket p prime, momentum eigenket. This can be any general ket, any ket. So let it be momentum eigenket. So then this equation becomes bra vector x prime momentum operator ket p prime, which is the momentum eigenket, is equal to minus IH cross dou by dou x prime. Here also, right hand side also, instead of ket alpha, let me substitute ket p prime. So we substituted for ket alpha, ket p prime, momentum eigenket. Now on the left side, when momentum operator acts on momentum eigenket, we get eigenvalue p prime times eigenket, and this eigenvalue we can take out. So p prime times bra vector x prime ket p prime minus IH cross. Okay. Now what is this? This is nothing but the transformation equation. Transformation function. Component of momentum eigenket along position basis. Okay, this can be also called the wave function of momentum eigenket in position basis, or the transformation function. So let me use this symbol here. So p prime, which is an eigenvalue, times this function, transformation function. On the right side we have minus IH cross dou by dou x prime u p prime x prime. Okay, our aim is to get an expression for this transformation function. So next what I am doing is, let us multiply both sides with the dx prime. Okay, now this quantity, derivative of a function with multiplied by the increment, small increment in the variable, independent variable, this gives the change in the function. Let us say du x prime. Let me use this symbol. A small change in the function. So rate of change of the function with respect to a variable times the small change in the variable will give you from the definition of differentiation, will give you small change in the function itself. Okay. Let us rearrange the terms. Let us take this term to the right side, this up x prime to the right side, then it will end up in the denominator, and take this minus IH cross to the left side, so that it will end up in the denominator here. Okay, and minus I, if I take to the numerator, it becomes plus I. So with these changes, what you get is I p prime by h cross dx prime. Okay, these minus IH cross taken to the left, minus I is comes in the numerator, then it becomes plus I. We have p prime dx prime. Okay, and this u p prime x prime is taken to the right, so we have du p prime, there is a p prime here, x prime divided by u p prime x prime. Okay. Now let us integrate both sides. Okay, let me write this result here. Okay, the right hand side, let me write here. What is the integral du p prime by u p prime x prime? It is natural logarithm of u p prime x prime. What about here? I p prime by h prime. P prime is an eigenvalue. Okay, so h cross so not h cross prime, just h cross. Okay, so these are all constants. This is an eigenvalue p prime. So this is a constant, we can take it outside. Integral dx prime is x prime. So what you get is I p prime by h cross x prime plus some constant c. Okay, so we have done this integration, we get this. Then again we have to get the expression for u p prime x prime. For that, let's take the exponentials on both sides. So left hand side becomes u p prime x prime equals, right side we have exponential of this thing. So we have e raised to I p prime by h cross x prime into e raised to c. E raised to c is a constant, so exponential of c is another constant. So we can write this as some exponential of c, let me write as some constant n e raised to I p prime by h cross x prime. Okay, now this n can be interpreted as the normalization constant. So let us evaluate this normalization constant. So in order to calculate this normalization constant, we can use the orthonormality of position eigenkets and also the completeness of momentum eigenkets. Okay, so we are changing from position basis, position eigenkets to momentum eigenkets. Okay, we are trying to find out the transformation function. So these position eigenkets are orthonormal and complete, momentum eigenkets are orthonormal and complete. So I am going to use the orthonormality of position eigenkets and completeness of momentum eigenkets to get this normalization condition. So yeah, so let us start like this. This x prime, x double prime. This is the inner product between two position eigenkets. Now let me introduce identity in between and use the completeness condition of momentum eigenkets. Okay. Then we have integral dp prime, bra vector x prime. In between these two, I am introducing momentum eigenkets. So we have p prime, then x double prime. This integral dp prime, get p prime, bra vector p prime is identity. I have introduced the normal orthonormality of position eigenkets and the completeness of momentum eigenkets. Left hand side, position eigenkets are orthonormal, so we get Dirac delta function here. Okay, and on the right side, what is this term? This term is same as this one, right? This u p prime x prime is nothing but this. So this is we get n e raised to I p prime x prime by h cross. Now what about this term? This term is, see, look at this term. This term is, if you interchange the two factors, we get x double prime p prime star. But what is this term? It is same as again this one, this transformation function, component of momentum eigenkets in position basis. Only change is that now instead of x prime we have x double prime, that's all. Okay, so we get the same expression with x prime replaced by x double prime with complex conjugate. Okay, so we have n star e raised to, this becomes minus I p prime, instead of x prime we have x double prime by h cross. Okay, so look at this. This is transformation function. We have substituted that. This is the complex conjugate of transformation function, correct? With with a different base variable x double prime. So we have complex conjugate of this one with x prime replaced by x double prime. This becomes n star and this becomes minus I here. Okay, now this n times n star is mod n square, we can take it outside, integral dp prime, and this two we can combine, we can write this as e raised to I p prime by h cross x prime minus x double prime. Now the question is, what is this integral? Okay, the limits of integration are from minus infinity to plus infinity. We are considering momentum components along x direction, so it can be from minus infinity up to plus infinity. Now this result, this integral this integral is actually one form of Dirac delta function. Dirac delta function can be expressed in different forms, and this is one form of Dirac delta function, this complex exponential form or the integral form of Dirac delta function, and the result is 2 pi h cross times delta x prime minus x double prime. When you have x prime minus x double prime here, Dirac delta function variables are again x prime minus x double prime. Okay, we will look at this result separately. This is a property of Dirac or a form of Dirac delta function. So let us quote this result now. In this integral is equal to 2 pi h cross times this. What is on the left hand side? On the left hand side you have this Dirac delta function coming from the orthonormality of position eigenkets. Okay. So remember that in this calculation of normalization constant we have used the orthonormality of position eigenkets, and we have also used the completeness of momentum eigenkets. Okay, now here delta function will cancel on both sides, so we have mod n square times 2 pi h cross is equal to 1. It means this n is equal to 1 by square root of 2 pi h cross. Okay, then our transformation function u p prime x prime is 1 by square root of 2 pi h cross times e raised to I p prime x prime by h cross. This is our transformation function. Okay. And this is also equal to, according to this notation, component of momentum eigenket in position basis. So this result is a very fundamental result. We will use this transformation function often, and understand the importance. This is the matrix element of the unitary operator that introduces the transformation from position basis to momentum basis. From the old basis is position basis, new basis is momentum basis. And these matrix elements are continuous functions. Okay, we can call them transformation function, and this is the form of that transformation function. Let us consider a few more points about this transformation function. We know that this transformation function produces the transformation from x basis to position basis to momentum basis, right? Or from x basis to p basis, a unitary transformation, and the matrix element of this unitary transformation is this transformation function. Okay. Now when you come from the x basis to p basis, this momentum basis is these are the eigenkets of momentum operator. Okay, so we move from position basis to eigenkets of momentum operator under this unitary transformation. And naturally, this unitary transformation will diagonalize the momentum operator. That means when you write the matrix of momentum operator in this basis, okay, then these are the eigenkets of momentum operator. So when you write the matrix of an operator in its own eigenkets, that matrix will be diagonal with the diagonal elements as the eigenvalues. So when you write the momentum, it's an infinite dimensional matrix for this momentum operator because it's an infinite dimensional space. So when you write the infinite dimensional matrix of momentum operator in this basis, since these are the eigenkets of momentum operator, we get the diagonal matrix. So this unitary transformation diagonalizes the matrix of momentum operator, right? So remember that when you have a unitary transformation that diagonalizes the matrix of an operator, then what will be the structure of that unitary operator? What will be the matrix of that unitary operator? Each column of that unitary operator should correspond to the eigen components of the eigen function of the operator P. We are diagonalizing this matrix, right? The momentum matrix, right? The matrix of the momentum operator. Then each column of this unitary operator should be the components of the eigen functions of momentum operator corresponding to each eigenvalue P prime, P prime, P double prime, P triple prime, etc. P1, P2, P3, etc. So each column of this matrix should be the components of the eigenfunction corresponding to one eigenvalue. Okay. Again, understand that another interpretation for the matrix element of this unitary operator, this is the matrix element of this unitary operator. Another interpretation is that it is the component of eigenket of momentum operator in the x basis. Okay, or in other words, this can be called the wave function of momentum operator in the x basis, or it can also be called the eigenfunction of momentum operator in the x basis, because these wave functions are eigenfunctions. We are taking the functions of eigenkets, right, in the components of eigenkets in the position basis. Components of eigenkets are called eigenfunctions. In one of the previous classes we have specified that. So since these are components of eigenkets, we can call them eigenfunctions. So these are eigenfunctions of momentum operator in the x basis, right? This is for the column x prime. See, for the row x prime. See, in a matrix element, this is the row index and this is the column index, right? So in first row or x prime row, we have the eigenfunction corresponding to the component of eigenfunction corresponding to p prime. When you go to the next row, okay, this is the column index. So we are considering the p prime column. So all the terms in this p prime column of this matrix, okay, will correspond to the components of this eigenket in the position basis, right? These are the components of eigenfunction corresponding to this position basis, and these eigenfunctions are eigenfunction is corresponding to the eigenvalue p prime. Okay, so this is the one row index. When you go to the next row index, column index is remaining fixed. Okay, so from the point of view of the diagonalization of momentum operator into the momentum basis, this unitary operator from our previous discussion on diagonalization, we know that the structure of this unitary operator should be that each column should be an eigenfunction of the momentum operator. And from this notation also, from the interpretation of this notation also, from our definition of wave function also, we know that this is the wave function of momentum eigenket in position basis, or this is the eigenfunction of momentum operator in the position basis. Okay, so naturally it's clear that each column, this is row index, this is column index. So if you fix the column index, each column should correspond to the components of the eigenfunction for a particular eigenvalue. Okay, this is the idea. And one more point is, if you take the complex conjugate of this one, okay, u p prime x prime star, this is, you can reverse the matrix element or this inner product. So we have p prime x prime, and this is equal to 1 by 2 pi h cross the complex conjugate of this one, e raised to minus I p prime x prime by h cross, right? But look at this. This can be interpreted as the component of the eigenkets of position operator in the momentum basis, or we can say the eigenfunction of position operator in the momentum basis, or we can use a notation for this one as u x prime p prime. Okay, so we have this result, u star p prime x prime is u x prime p prime. Okay, I hope you understand the idea. This is u p prime, that is eigenfunction of momentum operator in the position basis, and this is the formula. When you take the complex conjugate, okay, we get p prime in a bra vector p prime kept x prime. On the right side we have this complex conjugate, but this is the component of position eigenfunction eigenkets in the momentum basis. In other words, this is the position eigenfunction in momentum basis. Okay, so our results, if I summarize, the momentum eigenfunction in position basis is 1 by root 2 pi h cross e raised to I p prime x prime by h cross. Also, the position eigenfunction in momentum basis is 1 by square root of 2 pi h cross e raised to minus I p prime x prime by h cross. In other words, these are complex conjugate of each other. If you take the complex conjugate of this one, you get this. And this is can be written as bra vector x prime ket p prime This can be written as P prime x prime. This gives you the transformation matrix from matrix element of the transformation matrix from the x basis to p basis. This gives you the matrix element of the transformation matrix from the p basis, momentum basis to position basis. Okay, so this is the idea about transformation function, and this transformation function from, if it is from x basis to p basis, it can be interpreted as momentum eigenfunction in position basis. Okay, and this is the form of that. Okay. Now in the derivation of the transformation function from x basis to p basis, we have used a particular integral form of Dirac delta function. I'm sure you might have studied this in your mathematical physics course. Dirac delta function you have studied, but for those who are not familiar with how we obtain this expression, let us briefly look at it. Suppose you have a function f of x and its Fourier transform, let us say it is g of k. Okay, then Fourier transform g of k you can define as 1 by 2 pi integral minus infinity to plus infinity f of x e raised to I kx dx. This is the definition of the Fourier transform. And the inverse Fourier transform is f of x equals 1 by 2 pi integral g of k e raised to minus I kx dk. This is the inverse Fourier transform. Let's call it equation 1, equation 2. Okay, this is called Fourier integral theorem, and let us use this to prove to obtain the integral form of the Dirac delta function. So what we have to do is from equation 1, in equation 1 you have an expression for g of k. Let us substitute that expression here. Okay, so let us use the equation 1 in equation 2. So we have 1 by 2 pi integral. Let me write this first, dk e raised to minus I kx. Okay, I have written this first, and instead of g of k I am substituting this. Okay, it's 1 by root 2 pi here. Okay, the definition of Fourier transform, it is 1 by root 2 pi. Okay, so when I substitute for g of k, you have to substitute this one. Okay, so this is 1 by root 2 pi. Now when you substitute for g of k, you substitute equation 1. So then there is an additional 1 by root 2 pi here, integral. Then we have to substitute this. But already x appears here. So let us use another dummy index, dummy variable x prime. So here let me use x prime. So f of x prime e raised to I k x prime dx prime. This is for g of k. I have substituted equation 1 for g of k. So 1 by root 2 pi and 1 by root 2 pi we can combine as 1 by 2 pi integral. Okay, now here this is integration over x prime first and then integration over k. But this x prime and k are independent variables, so we can interchange the integration. So let us first do the integration over k and then do the integration over x prime. So let me take the terms containing x prime here, integration over x prime, integral dx prime f of x prime. This term also contains x prime, but it involves k also. So it cannot be taken outside the k integration. So what are the remaining terms in k integration? Integration over dk, and this term we can combine. So then we get e raised to I k x prime minus x d. Okay, dk I have already written. Okay, and the left hand side we have f of x. Okay. Now look at this expression. Let me rewrite this as f of x equals integral minus infinity to plus infinity f of x prime dx prime into, let me take this 1 by 2 pi also inside, integral e raised to I k x prime minus x dk. Okay. That means under this integral, when this function f of x prime is multiplied by with this term in this curly bracket and integrated over x prime, we get f of x. Okay. So it's as if in this integration over x prime from minus infinity to plus infinity, this term picks out only one value of f of x prime, where f of x prime is equal to x. Okay, the integrating variable here is x prime. When you integrate this right hand side, what the result is f of x. That means out of all possible values of x prime from minus infinity to plus infinity, we get exactly the value of x prime, the value of the function at x prime equal to x. So this term in the curly bracket acts as a selector. It picks out under an integral, it picks out one particular value of the function at a particular point x prime equal to x. Now this behavior is that of a Dirac delta function. We know that a property of Dirac delta function is integral f of x prime delta x minus x prime dx prime. This must be equal to from minus infinity to plus infinity, integrating over the entire x-axis. That means when you multiply this function, Dirac delta function, and integrate over the entire x-axis, then this Dirac delta function will pick out only one value of the function, which is x prime is equal to x. So we get f of x. So we compare, let us say this is equation 3, this is equation 4. You compare equation 3 and equation 4. Okay. So from the integral over f of x prime, in order to get f of x, you have to multiply this with Dirac delta function. So this term in the curly bracket is the expression of Dirac delta function. So comparing these two, we can say that 1 by 2 pi integral e raised to I k x minus x prime dk is equal to delta x minus x prime. Okay, this is the integral form of Dirac delta function. Now the result that we have quoted in the transformation, in the derivation of the transformation function, involves not k but momentum variable p. But we know the connection between momentum variable and k, which is the wave number, that is p equals h cross k. Okay, then if you take the differential on both sides, dp equals h cross dk. So we can substitute for k as p by h cross and dk as dp by h cross. Then this expression becomes, then I can substitute p by h cross, dk equal to dp by h cross, then that h cross will come out. We can write 1 by 2 pi h cross integral e raised to I p by h cross x minus x prime, dk is dp by h cross, and okay, h cross I have taken outside. This is delta function. We have used this result, okay, in the form of in the derivation of transformation function. Okay, simply replace k by p by h cross. That's it. So this is the integral form, either this or this. We can say just the difference is only that of a constant. Just k is replaced by something by x cross. Okay, so either this or this can be used as the integral form of the Dirac delta function, and this we have used in that derivation.